morning, this is K Devender Reddy, Assistant Professor in EEE Department in Staff Aeronautical Engineering. In this video, we are going to discuss about starting methods of three-phase induction motor, both the types like a squirrel gauge induction motor as well as slip ring type of the induction motor. If we look at the equivalent circuit diagram of three-phase induction motor, at the time of starting, the behavior of the induction motor will be similarly a transformer with a short-circuited secondary winding, because at the time of a starting, rotor is stationary and the EMF due to rotation is not developed. That is, the induced EMF in the rotor due to the rotation will not develop, and hence motor draws a high starting current. That means at the time of starting, the short-circuited secondary how behaves in a transformer, the similar behavior will also be there in a three-phase induction motor at the time of starting. So when you apply a full rated voltage to the stator winding at the time of starting, the rotor is shorted and there is no slip factor, means rotor at stationary condition and the magnetic field is rotating with a 1500, for example, if it is a 4-pole machine, it is rotated with a 1500 RPM, or else it is the term called it is rotating with a synchronous speed. When it is rotating with a synchronous speed, the magnetic field developed by stator winding is rotating with a synchronous speed. At the time, the magnetic field will be revolving and the stationary object called rotor is stationary. So according to the Faraday's laws of electromagnetic induction, the maximum rate of change of flux cutting by the conductor will come into the picture. At this point of time, the induced EMF in the rotor circuit is maximum. So a short-circuited secondary with a maximum voltage will also be circulate the more amount of current in the rotor circuit. So the rotor will needed more amount of current at the time of the starting. Similarly, the stator will draw the more amount of current from the supply side. So that is why it is a similar action. Whatever the things will be happened in the transformer short circuit test, the similar things also be happen in the case of the induction motor at the time of starting. That is why, to avoid the starting high currents, to avoid the starting high inrush currents into the stator, we will use a starter to limit the starting current for three-phase induction motor at the time of starting. Similarly, we used the starters for DC machines. Whatever the type of the starters we used for AC machines is different, but the purpose of the starter here it is similar with the DC machines called to limit the starting current for stator winding of three-phase induction motor. So here we have different type of starters for both the type of the machines, like a squirrel gauge structure, squirrel gauge induction motor, as well as the slip ring induction motor. So when we are going to talking about the starting methods for a squirrel gauge induction motor, we have three main considerations. When we're talking about the starting methods choosing for a particular type of the machine, we have to consider, or we have to consider the three considerations. The number one is a particular type of starter is selected on the basis of power capacity of the power lines. So based on the power capacity, which kind of starter is suitable for the induction motor, we have to consider that point. The second point, the type of starter selected on the basis of the size and the design of the parameters of the motor. Third one, the third consideration is type of the load on the motor, that is, load may be heavy or light. So when we are going to select a particular starter, we need to remember these considerations. So when we're talking about the selection of the starter, we should remember the power capacity of the power lines. The particular type of the starter is suitable for that power capacity of power lines. The type of the starter is selected on the basis of the size and the design of the parameters of the motor. And the third consideration is the type of the load is connected to that particular motor, whether it is a light load or heavy load, it is connected. So according by the above considerations, we can classify the starting methods for a squirrel gauge induction motor into two types on the basis of voltage. The two types are full value or full voltage starting method, and the second method is reduced voltage method for starting the squirrel gauge induction motor. Full voltage starting method and reduced voltage starting method for a squirrel gauge induction motor. Under full voltage starting method for squirrel gauge induction motor structure, one of the starting method is called direct online starting method, we are also called as a DOL starter. Under full voltage starting method for a squirrel cage induction motor, one of the type of the starting method is direct online starting method, which is also called as DOL direct online starting method starter or DOL starter for starting the squirrel cage induction motor. So direct to online starting method for a squirrel cage induction motor, the name itself indicates it is directly connected to the line. The motor at the time of the starting, we know it draws very high starting current, which is about 5 to 7 times of your full load current for a very short duration of time. Such a high value of current causes sudden undesirable voltage drop in the supply voltage. Now let us derive the expression for the starting current as well as the starting torque developed by three-phase induction motor at the time of the starting when we apply the full voltage to the starter or direct online switching. So for that we will assume the parameters we are using for the derivation. Now let us consider the TS is a starting torque and IF is a per phase rotor current at full load condition. IS as a per phase rotor current at the time of the starting. SF is a full load slip. SS is a starting slip. R2 as a rotor resistance. WS is a synchronous speed of the motor. Now we can directly write the expression for the torque of the induction motor as T equal to I square R by Ws into S. Or we can also write down the expression for torque. Generally we know the torque expression T is equal to, what is the T equal to, we have a formula P equal to T times of omega. P equal to T times of omega, where for the case of the rotor, I am assuming it as a P2 equal to T times of omega. So omega is that is the synchronous speed of the induction motor. P2 represents the rotor input current, and T equal to P2 by omega S. We can also write down the expression for torque, that is P2 T equal to P2 by omega S. That is P2 equal to rotor input power. It is rotor input power divided by the speed of the induction motor, that is angular velocity omega s. So we can also write down the expression for rotor input power equal to rotor copper losses by slip times into omega s, that is speed of the induction motor. So this expression is nothing but T equal to rotor copper losses per phase quantity, that is I square R divided by omega s speed into slip factor, that R may be a rotor resistance here. R will be a rotor resistance. You can also naming with the letter capital R to also no problem in this expression. So torque, we can directly write the expression torque of the induction motor equal to I square R by speed of the induction motor, that is omega s, into slip times. So from the help of the above equation, we can write the ratio of starting torque to full load torque that we have to know here. The starting torque TST equal to the starting torque. Torque is from this expression. Torque is proportional to starting torque equal to I square R. Let it be R2 divided by omega s into slip becomes 1 at the time of starting. Slip equal to 1 at the time of starting. So torque is proportional to TST, starting torque is proportional to where assuming as R2 as a constant and the speed anyway it is constant, slip becomes 1, it is directly proportional to square of the starting current, that is IST. Similarly, the torque at full load condition TFL, torque at full load condition, which is equal to current at full load condition, that is IF square into R2 by omega S into S times, where slip equal to other than 1 because it is under running condition. At the time of the full load, slip is in between 0 to 1, so we cannot confine, then it is a 1. So TFL is proportional to torque at full load condition is proportional to where R2 is a constant and IF square, current at full load condition, square divided by slip times. So this is equation number 1. Torque is proportional to the starting current square at the time of starting. The torque at full load condition, it is directly proportional to the square of the full load current, and also it is inversely proportional to the slip. So from the above two equations, ratio of starting current to full load torque, ratio of starting torque to full load torque, TST by TFL, which is equal to TST is IST square divided by IF square divided by S. So it becomes IST by starting current by full load current IFL whole square times of slip. So at the time of the starting, the torque developed by three-phase induction motor when it is directly switched on to the supply, TST equal to IS, that is starting current by full load current IFL whole square times of slip at full load condition into torque at full load condition TFL. This is a equation we are derived from the torque relations. When the induction motor is directly connected to the supply, means it will draws the starting torque equal to ratio of starting current to full load current square times of slip at full load condition into torque at full load condition. So next category under reduced voltage method for starting of squirrel cage induction motor. In reduced voltage method, we have three different types of the starting methods. One is stator resistor starting method, auto transformer starting method, star delta starting method. The first one is a stator resistance starting method or stator resistor starting method, auto transformer starting method, star delta starting method. First of all, we'll look into the stator resistor starting method. So it is very simple method to start the three-phase induction motor to limit the starting current at the time of starting. So simply we have used starting resistors, that is a variable resistors are connected to the each of the phase. Let it be, this is R phase, this will be Y phase, and this will be P phase. For each of the resistor, it is a variable resistor. We can also call it rheostats. The suitable range of rheostats are connected to the each of the phase, right? Three-phase AC supply is connected across the TPST switch. This is triple pole single through switch, TPST switch. So in between the stator winding and the three-phase AC supply, we are connected three rheostats or variable resistors to limit the starting current for three-phase induction motor at the time of starting. So at the time of the starting, these variable resistors or rheostats kept at maximum resistance position to limit the starting current drawn from the supply by the stator winding. Once it attains the sufficient speed, that is, once it attains the 50 to 70% of the rated speed of three-phase induction motor, then slowly cut down these resistors which are connected in series with each of the phase. Once it will be start rotating and it reaches these 50% to 70% of the speed, you can slowly cut out these resistors, and then direct supply will connect to the stator winding. So now it will be, there is no question of the high starting current drawn from the supply when you are using the resistor bank or a variable resistors in series with each of the phase of stator winding. So in this method, so the similar similar equations we will derive for stator resistor starting method as well, and we know the torque is equals to torque of the induction motor is equal to I square times of rotor resistance divided by omega s, that is angular velocity, into slip times. When it is starting, that is T becomes TST and S becomes 1 it is. So TST is proportional to square times of starting current, that is IST, right? This is equation number 1. So from the above expression number 1, we can also write down the expression for torque at full load condition TFL equal to I at full load condition IFL square divided by slip at full load condition, it is proportional. So this is equation number 2. So from these equations, we will directly derive the expression for ratio of starting torque to the full load torque TST by TFL is equals to ratio of IST square divided by current at full load condition IFL square, and it is slip times. So it is equal to TST by TFL is equals to IST by IFL whole square into slip at full load condition, that is SF. This is the final expression for the starting ratio of starting torque to the full load torque of three-phase induction motor when we are starting with resistor starting method. Now at the time of the starting the three-phase induction motor with the help of the resistor starting, the voltage is reduced by some x times of the V1 because of the resistors are connected in series. So resistors are connected in series with each of the phase. So obviously there will be a voltage drop across the resistors. That will be, I am considering here, x times of the V1 is the voltage drop in each of the phase at the time of the starting. So similarly, current also reduced to x times of the that starting current and x times of your what we called at the time of the starting. So we can derive the expression what we have in the previous case, that is TST by TFL equal to, we have the general expression that is current at starting by current at full load condition whole square into slip at full load condition. But because of the resistors are connected in series with the each of the phase, the voltage drop is some fraction of the voltage applied, that is x times of the voltage applied. Similarly, it also reduces your current to x fraction. So x times of the current at starting will be reduced because of the resistors are connected in series because of the starting resistor method into slip times of the full load. So we can write down the expression TST by TFL, ratio of starting torque to full load torque is IST by IFL, ratio of starting to full load current square times of slip at full load condition into x square times. And this is the expression for ratio of starting torque to full load torque when we go with resistor starting method. But this method is little bit, what we called, in this method we will lose some of the efficiency because of the resistors are connected in series. So there is large amount of power is wasted in the form of the heat at the time of a starting. But you can instantly disconnect these resistors when it attains the sufficient speed for a three-phase induction motor. The next method is auto transformer starting method. So it is also comes into the reduced voltage starting method for squirrel gauge induction motor. So when we're talking about the reduced voltage or when we're talking about the squirrel gauge induction motor, all these starting methods are referred to the stator side, not down to the rotor circuit. All the starting methods are at stator side. So in this starting method, auto transformer starting method, the name suggests itself we connect an auto transformer in between a three-phase power supply and induction motor. And all of we know how to regulate the voltage with the help of the auto transformer that we already covered in previous previous subjects like three-phase induction. We will covered in a previous subject, that is transformers topic. We will covered already the what is the function of the auto transformer, how it will regulates the voltage with the help of all the tappings which are there in a primary winding and secondary winding. So in the case here we will use a 3.3 phase auto transformer in between your supply as well as the stator. In between your supply and the stator we are connected a three-phase auto transformer. This will be a three-phase your auto transformer. It is connected to the supply. This is your supply, three-phase supply RYB. It is connected to the three-phase auto transformer. From the three-phase auto transformer, we will connect each of the phase to the stator winding of three-phase induction motor. Here I am showing star connected stator winding of the three-phase induction motor. So each of the phase is connected to the each of the phase of stator to the auto transformer, each of the phase. So with the help of the auto transformer, the voltage supplied to the transformer is reduced to x times of the supply voltage, and similarly current also reduced to x times of the starting current. So with the help of the auto transformer, we will slowly increase the voltage to the stator winding of three-phase induction motor, which slowly attains the maximum speed. So due to this, it will not draw the more amount of starting current at the time of a starting. So here, because of the auto transformer, the voltage supply voltage is generally we expressed in terms of the V1. It is reduced to X times of the V1. That X fraction represents the drop in voltage, or you are applying the reduced voltage with a fraction of X. And similarly, current also reduced from Is to X times of the Is. So after motor reaches its normal operating speed, the auto transformer is disconnected, and then full line voltage is applied to the stator winding. And these expressions are similar, like a previous case, what we derived in the uh, direct online starting as well as the resistor starting. We have a relation for ratio of starting torque to the full load torque is this one. The equation number 1 is similar for the previous cases. So when we're talking about the auto transformer starting, the voltage is reduced from V1 to X times of the V1, and current also reduced from IS or starting current from Is to X times of the Is. So this is the expression we will have for ratio of starting torque to the full load torque equal to Is by If whole square into Sf into X square. This is the similar expression we will have in a previous session, previous method as well. That is, in a previous method, that is stator resistor starting method, also we have the similar expression we have. So the reduced voltage starting methods, in the reduced voltage starting methods, we were finished two types. One is the stator resistor starting method, auto transformer starting method. The next method is star delta starting method for squirrel gauge induction motor. The star delta starting method for squirrel gauge induction motor. So the from the name itself, we will understood the what kind of method it is and how we'll connect the stator winding at the time of a starting and at the time of a running. And we have a relation V phase in the case of the star connected winding. We have a relation V phase equal to VL by root 3, right? In the case of the delta, we have V phase equal to VL, and similarly current relations are I phase equal to IL in case of the star connected network, and in a delta connected network, I phase equal to IL by root 3 in case of delta connected network. So there are total 6 terminals from the stator winding we have, each of the phase having the 2 terminals, starting end as well as the end part, that is ending starting terminal and end terminal. For each of the phase, we will have 6 terminals on a terminal box. So we will connect according depending on requirements, whether it is a star connected stator winding or a delta connected stator winding, with the help of the 6 terminals which we have in a terminal box. So here, at the time of the starting in this method, our intention is to limit the starting current. So this method is designed to operate in delta connected winding. The terminals are marked for the phases of the star as shown in the above. Now let us see the network how it will be operating. So see here, at the time of the starting, the stator winding is connected as a star connected winding. So at the time, the per phase voltage applied to the stator winding is VL by root 3 times. VL by root 3 times. So the reduced voltage is applied. It is the reduced voltage is applied. The reduced voltage is applied across the stator winding when the stator is star connected at the time of a starting. Once it attains the normal speed, the stator winding is now shifted to the delta connected winding. So the automatically there will be a TP-DT switch we have, triple pole double through switch we have. So this triple pole double through switch, when it is started with the help of the triple pole double through switch, it will make it as a star connected stator winding. Once it attains the normal operating speed, this triple pole double through switch is now switched to the delta connected network. So instead of it is connecting with A, B, C is connecting with 1, it is now shifted to the capital A, capital B as well as the capital C. Now the stator winding becomes a delta connected winding under running condition. So these are the expressions are similar With the previous case, what we have the ratio of starting torque to the full load torque. But now the things are changed. The voltage at the time of the starting is reduced to VL by root 3, line voltage by root 3 times. That is a reduced voltage we have. Similarly, current also reduced by the similar fraction. So we have uh, the V1, here we are assuming V1 is the per phase voltage, and the starting current at the time of the star position is ISS, starting current at the time of the star connected network, which is equal to V1 by root 3 times, right? Next, when the stator is delta connected position, we have a starting current IST when it is delta connected network, that is V by Z, clearly represented. Starting current under delta condition is equal to root 3 times of the starting current at star connected network. So this is the case. From the above expression we can write the starting torque ratio of starting torque to the full load torque equal to 1 by 3 times of starting current at delta IST by starting, that is full load current, whole square into slip at full load condition. So the IFD, where IFD equal to full load current under delta connected stator winding is equal to starting current under star connected stator winding. And this is an expression we will find out the starting torque developed by a 3-phase induction motor when it is started with star delta starter. Another kind of the starting method for 3-phase squirrel gauge, 3-phase, another type of the starting method for a 3-phase slip ring induction motor. On the rotor side, it is exclusively for only slip ring induction motor, and this type of the starting method is not suitable for 3-phase squirrel gauge induction motor because the rotor is permanently short circuited in case of the squirrel gauge structure. But whereas in the case of the slip ring induction motor, the rotor, here I am giving a star connected rotor winding which is connected to the 3 slip rings. These are the slip rings we have, and each of the slip ring is connected through a brushes. We can connect the external resistors, or we can connect the external load to the slip ring induction motor rotor. So we can extract the energy from the rotor, what it will deliver. We can extract the energy from the rotor, whether it is connected to the electrical load, or we can also connect the external star connected rheostat banks into the rotor winding to increase the resistance of the rotor. That will helpful for us to increase the starting current, starting torque. That will helpful for us to increase the starting torque at the time of a starting. So we already know the torque relation. Torque is proportional to the slip and inversely proportional to the resistance under high slip region. That is, at the time of the starting, the torque is proportional to the slip and inversely proportional to the rest. And we know the importance. We know the features of slip ring induction motor. A special feature of slip ring induction motor, we can increase the resistance of the rotor, and we know in low slip region we have a relation torque is proportional to the slip and it is inversely proportional to the rotor resistance. And in high slip region, that is at the time of the starting, in a high slip region, torque is inversely proportional to the slip and it is directly proportional to the rotor resistance. So if you increase the rotor resistance at the time of the starting torque developed by the induction motor is also increases. There are directly proportional between torque developed by 3-phase induction motor as well as the rotor resistance. So if you want more starting torque at the time of a starting, we will choose a slip ring induction motor. The rotor is connected to the external resistors, external resistive bank, whether it is a star or delta connected, depending upon the type of the rotor winding we have. So in this starting method also, the slip ring induction motor, in the case of the slip ring induction motor, the addition of external resistance in rotor circuit. This will decreases the starting current and increases the starting torque and also improves the power factor of the induction motor. when you add external resistors in series with the rotor winding, this increases the rotor resistance. According to this relation, the rotor resistance is increases. Obviously, the starting torque of the induction motor is also increases, right? So, with the help of the external resistors connected in series with the rotor winding, we will limit the starting current into the three-phase induction motor. This is one of the beauty of the slip ring induction motor. We will control the starting current as well as we will increase the starting torque of the induction motor only at the time of the starting. If you permanently connect these resistor banks in a slip ring induction motor rotor, it will decrease the efficiency of the machine as well. That is why these resistive banks are connected only at the time of the starting, and once it reaches the normal operating speed, just you have to disconnect the external resistors which are connected in the rotor winding and short circuit the rotor slip rings with the help of TPST switch. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.